I'm Noah Kantrowitz. I'm a chefy dude. I'm known as Cantrin on Twitter and CodeRanger, basically everywhere else. I work at Bloomberg doing open source, but let's jump right in. So to lead off, this talk is going to be about secrets as they pertain to infrastructure. If you're looking for advice on browser extensions or web development, use 1Password or PBKBF2, but those are different talks. So let's talk about what defines a secret. You could treat all private information in an infrastructure as secret, but that would get unwieldy really, really quickly. So to keep us focused, we're going to look at a couple properties. One, secrets are going to be small, usually only a few kilobytes at most. They may control access to much larger amounts of information via encryption, but the secret part itself is going to be smaller. They're radioactive. That means that if they were released, something very bad would happen. And they're required. So generally, things like graceful degradation are not going to be an option, or at least are going to be a much lower priority. Four sort of kinds of secrets that we'll be talking about. When we talk about passwords in this talk, we're mostly talking about machine-to-machine authentication, but with things that were originally designed for humans. So some examples are database passwords, HTTP proxy passwords, or Linux login passwords. So humans also do use passwords, but they play by different rules. Humans are allowed to know a thing that they never tell anyone else. Computers aren't. In contrast to passwords, tokens are usually used for APIs built from the ground up for server-to-server, machine-to-machine communications. They also aren't usually able to be hashed. So they have to be stored in their raw form. You can't sort of cheat and just store the hash. Some examples of tokens include PagerDuty API credentials, OAuth API credentials, stuff like that. And then keys are similar, but they're going to be much larger. They're usually whole files. They have some formatting in them, headers, new lines, whatever. Examples include TLS keys and SSH keys. And then sort of those are the three main ones, but there's a long tail of other weird stuff. Sometimes you can sort of make them look and act like one of the other three and just ignore the rest, but sometimes, like say, HIPAA compliance, there's secrets in there, and nothing I'm going to mention today is going to touch those. Those require purpose-built tools specifically for that task. So now we know a bit about what type of secrets we're talking about. Let's take their temperature. Hot secrets or online secrets are things used in the normal operation of infrastructure. So things that a server needs to be able to access without human intervention. Let's say a web application talking to a database, it needs some way to authenticate to that database, but if an operator had to sit at the console and type in the database password every time a new web request came in, app's probably not going to work too well. Compare this against cold or offline secrets, where you still want to store them, but they're used very rarely, so you can put them behind a bit more of a wall. Examples include AWS master passwords or revocation certificates. The hot versus cold dichotomy is rarely 100% clear in practice. Most secrets and tools are going to fall somewhere in the middle, so let's take a small application cluster as an example. Spinning up a new host in that is going to probably need human intervention, so that's kind of on the cold side, but once the service is running, it's going to have to run automatically and autonomously, so that's more on the hot side. And within online or hot secrets, there's another subspectrum around how often the secret changes. Most traditional secret management systems are built for slow secrets. Once set, a secret value rarely changes unless there's a big emergency like an exposure or complying with industry standards like PCI DSS. Rotating a slow secret is going to be a human-initiated action of some kind, and it's usually annoying enough that you don't want to do it that often. The biggest example is TLS keys. We all know that they rotate every year or two, but day-to-day we think of them as being static. Compare this with some newer secrets platforms and tools which are bringing in the concept of automatic rotation. This means the system is going to regenerate and redistribute the secret in hours or minutes. So examples include OCSP stapling for TLS, which spins about every 15 minutes, or EC2 role credentials, which cycle every 6 hours. Within reason, the more often you rotate a secret, the more secure you are. Every time it's rotated, it sort of wipes the slate clean for things like brute force attacks or prior leaks. It does, however, require more coordination between the thing managing secrets and the thing consuming secrets, because the consumer has to understand expiration timers and how to do the refresh. So those are the properties of secrets. What about the properties of secrets management systems? The principle of least access, as it pertains to computer science, is usually attributed to Jerry Saltzer in this 1974 ACM paper. While mostly common sense, it bears strenuous repetition because it is ignored so often. In short, a service or tool should have only access to the secrets it requires and nothing else. The quality of a secrets management system should always be judged on these two main properties. First, how well it implements that principle of least privilege or principle of least access. And second, how much audit information it retains so that when things go wrong, and they will, you can figure out exactly what happened and how to respond. Other features are important too. They will make or break your use case for a specific tool or specific service, but these should always come first. All right, let's do it. Let's manage some passwords. Pretty cool, right? We've all done this. We all probably thought it was a bad idea, maybe not why it was a bad idea. So let's think about this. What went wrong here? So on the principle of least access, everything that clones our code now has access to our secret. This is probably not going to be least access. Our code is going to be in a lot of places that may not require that password. And on the audit trail, maybe we have audit logs on our Git server about who did clones and updates, but we have absolutely no idea who read this password. So we've whiffed on both fronts. Let's probably do something better. Before we talk about different tools, let's talk about attack surfaces. Each attack surface is an especially vulnerable point where we have to think about what an attack would mean, how it would be carried out, and how we defend against it. This is not an exhaustive examination of web application security. Again, that's a different talk. I'm just talking about sort of the points in an infrastructure where you need to defend against things. I usually use these 8 major levels of attacks to worry about. Brute force, if you're on the internet, you're going to see these nonstop. It's been happening for decades, and it's not going away. Fortunately, they're relatively easy to defend against. The 3 Rs, rate limit access, things like logins and API calls to hopefully slow down brute force. Restrict access to things. If it doesn't need to be on the internet, don't put it on the internet. Private subnets are a really cool thing, or firewalls, whatever you can use. And rotate secrets often. Every time you rotate it, if it was previously brute forced, who cares? Start over. You can also use technologies that are currently unbrute forceable, like AES or 4096-bit RSA keys, but remember that that's always going to be a moving target, and someone might be able to retroactively decrypt things in the future. The next and weakest threat, code leaks. This could have a lot of impacts to your business, but as far as we're concerned, from the infrastructure side, this shouldn't be a big deal. We all probably know that we shouldn't be hard coding secrets into our source, so if the code leaks, not a huge deal. This could be something like a git push oops, but oftentimes these are more subtle. Things like incorrectly configured error pages can slowly leak out 1 line at a time, things like that. So be aware of these, but hopefully everyone will have no problems. Next up is a backup leak. These are going to usually be a superset of code leaks because oftentimes the code files just end up in backups because who cares, but it'll also include databases, config files, etc. As an example, the Instagram hack a year or 2 ago, that was a backup leak. There was a backup file that had some credentials that people forgot about. The easiest way around these, store secrets in RAM or don't put your secrets in backups in some other way. Beware that when you're configuring don't store secrets in backups, that's usually an opt-in system. You have to explicitly list which files to exclude from backups. So always be aware when you're adding a new secret-y file that you have to go and update probably a whole bunch of places. Traversal attacks. So this is things like directory traversal or SQL injection. From an infrastructure level, what this means is there is a secret that the application or service has legitimate access to, that it really does need, but that the user accessing the application or service is not supposed to be able to access. So in this case, least access helps because anything that the application doesn't have access to, the user doesn't have access to. But again, you also need good web app security, tool security, et cetera in there. As an aside, a frequent traversal style attack takes advantage of the fact that people store secrets, usually API keys, in environment variables. This is so common, it is in fact considered a best practice by the 12-Factor Manifesto. I'm here to say maybe not so much. There are some problems with this. The biggest one, basically every exception and error logger sucks in every environment variable it can see and stores them in clear text in an error log somewhere. So that database password or API token that you just put so much work into protecting, now it's just chilling on disk on your error reporter. The other problem, they are inherited all sub-processes. So with something like, say, Chef or Puppet, where you're executing a lot of sub-processes, all of a sudden you have to worry what if any of those is compromised or evil. Here be dragons. I generally recommend avoiding them, but some people will have to use environment variables for things. Some tools only accept secrets via environment variables. All right, back onto our attack surfaces. Code execution. So now the attacker can run arbitrary code. No web app security can help at this point because they're not going through our web app's code. So really here we are falling back only on least access. Anything that the app or service has access to, the attacker now has access to. When Dante passed through the gates of hell, he notes the inscription, "Abandon all hope, ye who enter here." This is pretty close to a worst case scenario as far as we're concerned. Least access is the only thing that could protect us at this point, but the important thing is to know what the app had access to and therefore know what to rotate and how. Another commonly ignored attack surface is laptop theft. If you're at a small company, access to a developer workstation is probably root on every server. So everything we just saw on the last slide times the number of servers you have. Fortunately, laptops are used by humans, so we can rely on the fact that humans are allowed to know actually secret passwords and use tools like disk encryption so that access to a workstation doesn't give you everything. And then finally, the higher power attack surface. This is where a lot of people draw the line on planning, either because they don't want to or because industry regulations don't allow them to tell the FBI to smeg off. But things like FISA court warrants, state-sponsored hacker groups, etc. The list goes on. It gets increasingly difficult to handle the further you go. Here you'll have to ask yourself how far you want to go, how far you need to go, figure out what you're going to do. Let's talk about some tools. That was the theory part. More practice. Starting from the top again, manually moving around text files, what we saw before. Sometimes this will be checking things into your application's repository. Sometimes you'll have a standalone secrets repository. Sometimes you'll just copy files around. That last one, usually how people deploy TLS keys. But we've already talked about why this is bad, so next. The next step a lot of people reach for is let's encrypt it and then store it in Git. Gitcrypt is probably the best of these. There's a ton, but Gitcrypt is nice. But it comes with a lot of downsides. We still have no good way to implement least privilege, and we still have no audit logging because it's tied to access to Git. I mentioned in the last slide that Gitcrypt can either be symmetric or asymmetric, so let's define those terms. When you're using a symmetric system, that means that you're going to take some kind of secret, you're going to encrypt it with a key, you're going to get an encrypted blob, put that somewhere that the secret's consumer can access it, and then deal with getting the secret key over to the consumer. You might note here that that key is itself a secret. So we haven't actually solved a problem so much as just moved it down a level of recursion. This is as compared to asymmetric systems where we're going to generate a public-private key pair, RSA, elliptic, whatever, for each consumer separately. We're going to take the public keys and we're going to tie them each to the consumers that need to access a given secret. For each of those, we're going to generate a separate encrypted blob, again, put them somewhere that the consumer can access them, and then we don't need to actually get a separate key because the private key is already on the consumer. So what this means is that asymmetric systems, because you're generating a separate encrypted blob for each consumer, it's a little bit more flexible in terms of access controls, but it also means that you need to deal with mapping the identities, the public keys, onto each consumer. It's difficult, but in a different way. All right, back to tools. Being active in the Chef community, I see a lot of people trying to move from Git secrets to encrypted data bags, thinking it says encrypted, it makes me feel all warm and fuzzy, this will be great. But again, it's a symmetric system. We haven't actually solved any problems because we still need to deal with distributing this key. Chef does include some tools for this, but they're not very good. Ansible Vault is similar to encrypted data bags, but it takes advantage of the push-based nature of Ansible, so the decryption key is needed on the workstation running the push, usually by a human typing it into a keyboard. This is maybe a little better. We have to distribute the decryption keys to our developers, but not to the actual target machines. But at heart, it's still turtles, because we haven't actually solved this sort of key distribution mechanism. EML is probably the closest analog to encrypted data bags in Ansible Vault in the Puppet world. A key difference is that Puppet usually will do all of the decryption on a single Puppet master. So that means we're giving the Puppet master access to all secrets, and we're trusting it to only hand them out as we have configured within Puppet. This kind of secret silo is called a trusted third-party system. We'll see a couple more as time goes on. But in general, because it has access to all secrets, whenever you examine a TTP system, including EML, gut check your faith in its internal access control code, because that's really what you're depending on for limiting access. Back to a Chef-specific tool, Chef Vault, no relation to Ansible Vault. This takes advantage of the fact that Chef has an existing key system, RSA key pairs used for API authentication, and uses that to build a key distribution system. So we've solved the symmetric key distribution system by adding in a new key distribution system. Better, definitely better, but still a little turtley. There are tools for rekeying Chef nodes, but even those of you that have used Chef for a long time may not even know how to do that. All right, so we've seen a couple tools. Let's talk again a little bit about the theory. Pre-encryption systems versus trusted third party. So I said trusted third-party systems have access to every secret and just have to depend on code to figure out who's supposed to access what, whereas pre-encryption systems, you generate either one or many encrypted blobs and then depend on math. As you might expect, math that is rigorously tested is better than code, even when rigorously tested. So in general, a pre-encryption system is going to be stronger, but it means that you have to do all of the work of figuring out who is supposed to have access by generating those encrypted blobs ahead of time. This makes pre-encryption systems a little bit difficult to deal with things like auto-scaling and self-healing, because there may not be somebody hanging out to generate new encrypted blobs as a new machine comes up. So if you're looking at doing auto-scaling, you probably want to look at a trusted third-party system, or you're going to end up building one yourself. All right, leaving the realm of single CM tools, HashiCorp Vault, again, no relation to Chef Vault or Ansible Vault. They all just pick the same name. It's relatively new, but making a lot of waves in the secrets world. It's a dedicated secrets management platform, so it has all the features you'd expect: audit trails, granular ACLs, modular backends, et cetera. It also has a best-of-breed rotation system for fast secrets. Slightly older, but still solid, is Square's KeyWiz. It's got a little bit more of a limited data model, but that means it's a lot more battle-tested because it only does basically one thing. I'll talk more about KeyWiz FS later, but KeyWiz, as the name implies, excels at managing key type or whole file secrets. Before I talk about the next two, let's talk a little bit about Amazon KMS. Amazon KMS is not itself a secrets management platform. It is best probably characterized as a key escrow platform. So that means that you generate a key. This symmetric key lives in KMS, and you cannot remove it from KMS. But you can send data to KMS and get back an encrypted blob, and you can later send the blob up to KMS and get it decrypted. This is incredibly tied into the AWS ecosystem. In all of the things that use KMS, if you want to use them, you must be completely AWS forever for all time. That may not be a problem if you've already bitten off that whatever, but be aware it does tie you to that ecosystem. So Sneaker from Coda Hail builds on top of KMS to give you a sort of more complete tool. KMS itself doesn't do storage, so this is a command line tool that uses S3 for storing the encrypted blobs, dealing with syncing data back and forth, et cetera. And maybe slightly nicer, Confidant from Lyft. It uses KMS again, but it uses DynamoDB for storage. And instead of being a command line tool, it's API-based. So you run a Confidant service somewhere, and then you can talk to it over a REST API. A notable feature of this is it's got a really nice versioning and history system, so you can build provable logs of when and how secrets changed. Trousseau is an asymmetric pre-encryption tool, command line based, built around GPG instead of KMS. So you can use this on anything instead of just Amazon. It's got pluggable backends for storage, but being GPG-based for the encryption means that it's going to be a little bit more difficult to deal with key distribution if you're not already really familiar with GPG. GPG has some provisions for automation, but they're not great. Red October from Cloudflare is a bit of a different beast. Mostly we've been talking about things designed for hot or maybe tepid secrets. Red October is really built for cold from the ground up. It uses an N of M key split algorithm, similar to the old, you have to turn 2 keys at the same time to launch the nuclear missile systems. You can designate a secret as 2 of 3 or 3 of 5 or whatever you want. So you need that many people or key holders to coordinate to unlock a secret. This is really, really great for things like AWS master passwords, where you would need 3 employees. So if one person's laptop is stolen, we don't care. We need at least 3 people to unlock this secret. You could say 1 of M and use it for hot secrets too, but cold is where it really shines. Presented for completeness, Barbican was originally intended to be the OpenStack equivalent to Amazon KMS, but it's dead, sorry. I mentioned Conjur because I see it the most, but that may just be the sort of circles I move in. Really, this is representative of all other closed source tools. Be doubtful. If you can't verify somebody's security guarantees, assume they're false, and beware around closed source tooling. And finally, the biggest gun, hardware security modules, or HSMs, dedicated bit of hardware that holds a key that cannot be extracted short of opening the chip up with acid and reading it with an electron microscope. They're very expensive, very complicated, and if used properly, very unbreakable. But there's a ton of them if you want to go down this road because you have a lot of money and very, very bad things would happen if your secrets were revealed. Expect to hire some very expensive consultants. All right. Through all of this, we keep dancing around this really hard problem of secrets management. Deep down, any secrets management system will need to establish an identity relationship or authentication between the thing requesting secrets and the thing managing them. Turns out bootstrapping this relationship is really difficult. Usually it's going to be something of the form, I'm going to SSH and dump a key file on whatever answers for 1.2.3.4. And that person, that machine, will hereafter be known as X. If there was a network intercept or the machine was already compromised, we don't know what happened. Once you have bootstrapped the identity relationship, you can have nice things, but doing the bootstrap can be difficult. Individual clouds have tooling for this. So for instance, Amazon, the Amazon metadata service really, really knows who you are in a way that we almost entirely trust cannot be interdicted. However, some clouds like OpenStack don't have a solution for this, and if you're running on your own hardware, There are some solutions out there, but this is the sort of deep problem you're going to run into over and over. As a corollary, if you take it as a given that you need to build an identity management system in order to use secrets management, sometimes you can just skip the secrets altogether. A lot of things, MySQL, Postgres, et cetera, support TLS client certificates for authentication. As we saw with the asymmetric systems, public keys aren't radioactive. You still need to handle them very carefully and make sure that trust is maintained all the way along the usage chain, but you don't have to keep them private. This can maybe solve some problems. See how it goes. Let's quickly talk about some integration tooling. For tools that run their own service, so they're not a command line tool, they usually have API clients that you can use in a wide variety of languages. HVAC is in Python, Vault Rails, Ruby, Bodo Core Python, AWS SDK in Ruby. You can either use this from your application code itself, or you can integrate it directly into config management. You can also use your CM tool to run any of the command line tooling, just like you would anything else. KeyWizFS is relatively unique to KeyWiz, although there are Fuse drivers for some of these other systems, but KeyWizFS is probably the most battle-tested. In this case, it's a client implemented as a Fuse file system. This means that if you've got tools that you don't want to modify, say Nginx, you can tell it to read its TLS keys directly out of KeyWizFS. They will only ever live in RAM, they'll never get buffered to disk, and you don't have to actually modify Nginx to do this. Super cool. Console templates was originally designed for Console, the HashiCorp service discovery tool, but it's also been augmented to be able to read data from Vault. This is similar to doing the integration in your config management platform, but if you're either not using config management, although you probably should be, or you just want to run the refresh at a much higher rate than you're running config management, so you run Puppet every 6 hours, but you want to be able to refresh your secrets every 15 minutes, console templates can be a cool shim to sort of shove in there. Conf-D also lives in a similar space. End console, similar to console templates, but instead of generating files, this puts things into environment variables. You'll remember I said I don't really think this is a good idea, so, but if you need it, it's there. And then summon is similar to end console, but it's got pluggable providers for a bunch of different things. Again, it uses environment variables, here be dragons. All right, to sum up, check your privilege, check your audit trail, pick your types and temperatures of secrets, think about your attack surfaces, and have a disaster plan for what happens when all of this goes wrong, and you will have, hopefully, happiness in your secrets management. Thank you. Any questions? Yes? Sorry. Can I explain the turtles reference a little bit more? Is this, I think it's from Terry Pratchett, no. I think it was from a meeting with Terry Pratchett. Might have been Isaac Asimov, I don't remember. A famous author, I do not remember exactly which one, was once posed the question, that's a very nice story about how the world works, but I actually believe that the world is just it's elephants sitting on the back of a turtle. To which the person responds, well, okay, but what is the turtle standing on? There has to be something in space. There has to be physics, there has to be gravity. And the woman responds, that's a very clever answer. However, I'm sorry, it's turtles all the way down. So meaning you can't just solve problems by ignoring them if you just have turtles forever. Any other questions? Thank you very much.